Now today we're going to start the lecture 4, section 2.5, 3-wire single-phase residential wiring. This section shows the United States residential wiring. In United States, the frequency is 60 Hertz, and the voltage at home is 120 volt or 240 volt. And the section 2.5 will show you how the wiring is configured in the United States, so that at the United States, the home can obtain 120 volt and 240 volt. Most of the heavy appliances that use 240 volt, for example, the electric clothes dryer, the space heater, and those will be supplied using a special outlet at home, usually located in your garage. In the home, somewhere that nearby, there is a power pool. The transformer is mounted on a power pole, bring the voltage from 4.16, 4016 kilowatt down to 120 volt and 240. The question is how they accomplish that. Let's see the next slide. This graph shows a 3-wire single-phase power drop. This includes utility pole transformer. This is transformer. And then the 3-wire drop through the electric meter and also with a circuit breaker. The transformer, the primary side voltage is 4000 volt. And through this transformer, they have two lines. One is the center line is the ground line. By grounding the center tape of the second side, the transformer, the top winding, this is top winding, is 120 volt, and the bottom winding, this is a bottom winding, is a minus 120 volt. So this is a very smart design. So the bring these two together is a 240 volt. So the voltage difference between these two lines is 240. That is a special circuit to provide power supply for heavy appliance. And most of the home appliances are using 120 volt. This is have an inherent safety advantage. At any point in the home, the voltage between the voltage with the grounding is no more than 120 volt. So this is the safety reason, because the maximum voltage to kill a person is 120 volt. So because human being is a resistor, a big resistor, and any voltage above 120 can kill a person. Less than 120, people can still maintain alive. So this is the advantage of this configuration. How this 240 volt being created? We can use algebra to demonstrate the creation of 240 volt. The V1 is the top winding voltage. It's 120 multiply square root 2 cosine omega 2 pi omega t. And the V2 is the lower part, the bottom winding of the voltage, which is minus 120 multiply square root cosine 377 t. So the difference, V1 minus V2, is 240 multiply square root 2 cosine 377 t. So this is one way to demonstrate. The other way to show how this 240 volts been created is using the waveform. You can see this is the top winding voltage. This is the bottom winding voltage, and V1 minus V2 will become this waveform. We can show the magnitude is 240. Now section 2.6, three-phase systems. In home, we show it's a single phase, but the commercial electricity is almost always produced with a three-phase synchronous generators. Why we need to use a three-phase? There are two good reasons. Because first is a three-phase generator are much more efficient in terms of power per unit of mass, and the three-phase generator can operate much smoother with less vibration than single-phase generator. This is the first advantage. The second advantage is that the three-phase transmission and distribution system use their wires much more efficiently. So both from the generator side and the transmission and distribution side, they have two advantages. Let's see this in details. Section 2.6.1, balanced wine-connected system. As shown in this figure, if we have a three-phase system, if it is supplied the three-phase load, if each phase supply is on load, it requires have a two line. One is a sending wire, and the other is a returning wire to form a circuit. So if we have a three-phase, that will require 6 wires. But if we combine these together, we can use 4 wires. However, if VA, VB, VC are in the same phase, the neutral wire, the return wire, the common return wire, will equal to IA plus IB plus IC. When VA, VB, VC are in the same phase, and then this wire could carry more current than the supply wires. Now, here is the smart design. If we make each generator derive the same voltage, but with a 120-degree phase difference. So for example, VA is equal to V multiplied square root 2 cosine omega t. We assume the phase is 0. VB have a 120-degree more than VA, and VC is another 120-degree or minus 120-degree, because a circle is a 360-degree. So if VA, VB, VC, they have the same voltage magnitude, but with a 120-degree phase difference, we can see if we assume that the three-phase load, the load are also exactly the same, and also with the same phase angle. So we call this load as a balanced load. And this three-phase circuit is said to be a balanced circuit. Okay, so with balanced load, the current of each phase can be written as IA is equal to I multiplied square root 2 multiplied cosine omega t. So IA will be in the same phase as the VA with a 0 degree. IB with the same phase with VB with a 120 degree. IC with the same phase with VC with a 240 degree. Oh, then we add 1A, 1B, 1C together. The current flowing in the neutral wire is therefore equal to 0. So for a balanced three-phase circuit, there's no current in the neutral wire. In fact, for a balanced three-phase circuit, we even don't need a neutral wire. However, there could be the system is not always balanced, and also during if there's a fault between each phase, or there's a fault with the one phase to the ground, they will create unbalance for the three-phase system. They still need a neutral wire to be measured what could happen in the system. So it is true that if for a balanced three-phase system, we can even eliminate the neutral wire. So this is a typical design with a 4-wire, one connected generator, and also one connected load, the three-phase circuit. So the VA produced through this wire supply the load A, and the VB provide the wire supply the load B, and the VC provide the voltage supply load C. And the VA to the ground is the phase voltage, and the VAB is called the line voltage. So the voltage measured with respect to the neutral wire is called phase voltage, VA, VB, VC. Voltage measured between the phases are called line voltage, VAB, VBC, and VAC. The relationship between the line voltage and phase voltage for this winding connection is that VAB is equal to VA to neutral wire, VA0 plus V0B, which is equal to VA minus VA0 minus VB0. So be written in this equation is VA multiplied square root 2 cosine omega t minus VB square root 2 cosine omega t minus 120 degree. And we can calculate the line voltage. So the line voltage through this calculation and through when we apply trigonometric identity, we can obtain the V line is equal to the square root square 3 V phase. So the RMS value of line voltage is equal to the square root 3, the root mean square value of phase voltage. So the 4-wire 3-phase service to the building provide power of line is 208 volt. So this is a line voltage. We usually use the line voltage to describe the transmission system or distribution system. And the neutral wire serving as a reference voltage. The phase voltage is 208 divided by square root of 3 is 120 volt. So we can see the phase voltage is still 120 volt. For higher power demand, we use a line voltage of 480 volt, and which means the phase voltage is 277 volt. This is usually used for large commercial buildings. This graph shows the diagram of a 480 to 277 volt system. So this is the 3-phase, as we can see, wired in the using the Y shape. This wiring system, the phase voltage, this is a neutral wire. Phase voltage is 277 volt. The line voltage is 480 volt. The 480 volt is related for supply power for the motors, and the 277 volt is to supply the fluorescent lighting system. And between each wire, between this each phase, so during this line voltage, we add another transformer. This is a single-phase transformer to generate a 120 volt and a 240 volt. That's used to supply the the load with a lower voltage. To find the power delivered in a balanced three-phase system with a given line voltage, we need to consider three kinds of power. We have apparent power, real power, and reactive power. As we have explained or introduced this concept in the 2.4, the power triangle system. Now the total apparent power is 3 times of the apparent power in each phase. So the three-phase apparent power is equal to 3 multiply the V phase multiply I line, because in the Y connection, the phase current is equal to the line current. So the V phase is the effective value, or root mean square value of the voltage in each phase, and the line is a root mean square value of current in each phase. So the reactive power is equal to the square root 3 V line I line sine theta. The real power is a square root 3 V line I line cosine theta. And since the phase voltage is equal to line voltage divided by the square root 3, so the three-phase apparent power is equal to the square root 3 multiply the line voltage and the line current. So this graph shows the summation of the power in each of the three phases. We can see the total power, PA plus PB plus PC, is a constant value. And this really show the advantage of the three-phase power, which is they provide the smoother performance of motor and generators. But if for a single-phase system, we can see the power PA, PB, PC, they varies according to time. Therefore, will leading to a rougher motor operation. So the sum of the three-phase power in balanced delta 1 load is also a constant. It will be not a function of time. But we also can see there are different configurations between the generator and the load. The generator could have the Y connection and also have another connection called delta connection, which is the line voltage is equal to the phase voltage. And also in the load side, we also have a Y connection and delta connection. So for the current, if it's a Y connected, then the line current is equal to the phase current. However, the voltage, if it's Y connected, the line voltage is equal to the square root of 3 of phase voltage. For the power is equal to the square root of V line I line cosine theta. Theta is the phase difference between the voltage and the current. For delta connected, the I line is equal to the square root of the I phase. However, the line current is equal to the line voltage of the delta connected system is equal to the phase voltage. The phase current, the three-phase current, is also equal to the square root 3 V line I line cosine delta. So no matter whether it's a Y connected or delta connected, the power delivered from the generator to load will be the same, will be always equal to the square root 3 root mean square value of line voltage multiply root mean square value of line current multiply cosine theta. Theta is the angle between the voltage and the line. 2.7 power supplies. We have two kind of power supplies. One is we use traditional transformers to drop the voltage from the high end down to appropriate level to supply the load. Another way to provide power, when we have power electronic technologies developed, we can use the switching. The switching is a power supplies that skip the transformer, but the voltage conversion using a rapid on and off switching of a transistorized circuit. So this is another way to provide power. And the linear power supplies typically operate as a 50 to 60% range of energy efficiency. So we can see this amount of power being lost. The switching power supplies are closer to 70 to 80% energy efficiency. So these have a better energy efficiency. And also we can see from this graph figures comparing efficiency of 9-volt linear power supply for a codeless phone versus a switch mode supply. This is switch mode supply. This is the linear power supply. If we use a transformer to bring down from 120 volt down to the 9 volts. Another way is we use a switch mode to accomplish that. We can see that really for different current output, the switch mode power supply, they require less power, and also the range is very narrow. But for the linear power supply, they're going to spend more power or require more power, and also the range can be wide. So in terms of efficiency, the switch mode power supply have much better efficiency than the linear power supplies. Now we finish the section 2.7. The section 2.8 power qualities is a self-learning session, so will not be covered during our class. Now this will complete our lecture 4.